In this video, we're going to talk about how our data has spread or variation, is another way of saying that, and kind of look at some specific examples. So the first thing we look at is what's called the range, and that is the difference between the highest and lowest values. Let me zoom in a little just to make my writing a little bit easier to see. Difference between highest and lowest data. Now, the interquartile range, that's really specific, and it's primarily looked at when we're doing what's called the 5-number summary, which we're going to look at in just a second. So it is the difference in the middle 50% of the data. The standard deviation is special, and it is the most important of the three. And it's also the most complicated. The standard deviation is the average distance. The average distance a data value is from the mean. On average, how far data is from the mean, but a specific data value. Okay, so let's look at what's called the 5-number summary, and that actually has a direct connection to what's called a box plot, which you might have heard of or done. They also, I believe, call it box and whisker plot. You might have heard that used in high school. So the 5 numbers that make up the 5-number summary is the minimum, the Q1, which is referring to the first quartile, and as you can kind of see, quartile, we're talking about quarters. So we're talking about 25% of the data. And then there's the median, and then there's Q3, which is the third quartile. So I know you're probably wondering, where's the second quartile? Well, the second quartile is the median, because that's going to represent the 50% mark, marking the middle value. The third quartile is the 75% mark. And the median is Q2, and it's the 50% mark, right? That's what the median represents. Okay. It's pretty simple to find. Let's look at this data. And I think this is the same data we looked at in the previous section. So if it looks familiar, that's why. So let me just count it up real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yes. Okay. So there are 19 pieces of data, and therefore we're going to count to the 10th data value, and that's going to be the middle. So that is 74. All right. And that is our median, or Q2. But we don't call it Q2. We call it the median. The minimum would be the very first number. Oops. And the maximum, the last number. So then to find Q1, we're going to basically look for the median here in this first little group. We're going to look for the median here from here to here. All right. And in the first group, we're kind of using this 74 as the middle number. And our first group of data, let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we get 62 would be our Q1 here. And in the second data, looking for the middle number here in the lower half of the data, that is going to be 84. And when we write the 5-number summary, we can just write the numbers. So 49, 62, 74, 84, and 96. That is the 5-number summary. The range of the data is from highest to lowest. So that would be 96 minus 49, which comes out to 47. So that's the range of the data. They have a difference of 47. The interquartile range is the difference between Q3 and Q1, which we know that's 62 and 84. So we're going to do 84 minus 62, and that's 22, the middle 50%. That tells us something when it ends up being close to half of the range, because if it isn't, that means that we might have some skewing or possible outliers. Okay, so a box plot, the way we draw that is we always start by drawing a number line. And since we're looking at test scores, I think we'll just do kind of where we did the histogram. We'll go 50 by 10. So 40, 50, 60, 70. Oops, that's a little spaced off wrong. 80, 90, 100. Okay, I didn't need to go as long. Great, there we go. Okay, so 49 is the first value, and we'll put a dot at the minimum. Sometimes they like to put a line. I just use a dot. Highest value is 96, so that should be a little bit above 95, a little bit above that halfway point. The median is 74, and that should be right a little bit below the 75 mark, which should be like right about there. So I'm going to use a line to represent that one. Q1 is at 62. I'm going to use a line there. And Q3 is at 84, somewhere right about there. So I draw a box around the median, Q1 and Q3, and then I draw little lines to connect to the min and the max. And it kind of gives me an idea of the shape. Now, when I'm looking at it this way, it's very symmetrical. Okay. I can kind of see that our data is looking like the majority's here in the middle. We have a little bit above, a little bit below. It kind of looks real symmetrical drawn out this way. And when I look at it this way, I definitely would say it doesn't look like there are any outliers. So no, I wouldn't say there are. But if there were, that would probably mean my data would look very elongated on one side. So just to kind of give an example, like let's say there's somebody over here, we got 115, right? That's weird compared to everybody else. That definitely has this long extension, and that would be an outlier. But that is not how it looks. Okay, so if the data is symmetric, we tend to use the mean and the standard deviation. And if the data is skewed, we use the median and the IQR. Makes more sense in terms of getting accuracy, because the median happens to be resistant to outliers. And the reason is, if the outlier, like if this first number, like I said a second ago, happened to be 115, I'm sorry, the last number, if this was in fact 115, right? The median doesn't change. If this was 200, the median doesn't change. And that would clearly be an outlier compared to the rest of the data. So the idea is that the median doesn't change when there's an outlier. The mean, however, does change. The mean is affected by outliers. Which is why in the last section, when we were looking at how data is kind of shaped, the mean will be smaller than the median if we happen to have a lower outlier, and the mean will be bigger than the median if we happen to have a large outlier. Okay, now standard deviation is the average deviation from the mean. There is a way of approximating it, which is using the range divided by 4. But that's really when we're not looking at anything with outliers. So let's go ahead and find the standard deviation, and we are going to do it by hand. And I'm going to give us a table to kind of do this in. So we're going to step through this, and I'll show you the first few, and then I'm going to ask you to finish calculating them to compare your answers with me. And then you can kind of see what I got. So this is the formula we're going to use. Let's talk about this formula really quick. This symbol right here, oops, I hit the highlighter, but it hadn't highlighted by that point. That symbol right there in math means sum. So whenever you see that symbol in a math textbook, they're adding something together. When we see X in a formula for statistics like this, that is usually representing a data value. S in this case, that's representing our standard deviation, which I'm going to abbreviate. And then N is representing what we're going to call the sample size, or the size of our little group that we're looking at. So in order to find the standard deviation, we need the mean. See how it says mean? We need the mean. So we need to find the mean for this data right here. Now we did that already in the last section. If you want to go look it back up, that's fine. I believe it came out to 72.6, but I'm going to go ahead for ease. I'm going to round it to 73 just to make our numbers a little bit easier to work with. Because I'm rounding it, by the way, the standard deviation I'm going to calculate by hand is going to be a tiny bit different than if you were to use the calculator and all the decimals or a spreadsheet. Now, I'm not going to do standard deviation on a spreadsheet. I'm going to use the tables, so I am expecting you to do it by hand like this. Okay, so first thing we're going to do, and here I'm going to erase some of the stuff that's in my formula here. It's kind of messy. First thing we're going to do is we are going to subtract every data value from the mean. That's what this formula says to do. Take every data value and subtract the mean. So I'm going to take this very first data value of 49 and I'm going to minus 73. And when I do, I get negative 24. It's going to come out to negative 24 again, by the way, for the next one, because they're the same. Then I would do 52 minus 73, which comes out to negative 21. And I'm not going to keep writing these. I'm going to go ahead and just start calculating them. And if you want to take a second, put them in your calculator and calculate them too. That's great. This will be negative 15, negative 11, negative 7, negative 6, negative 2, 0, based on how I've rounded, 1, 2, 5, 8. This is going to be 9 and 11, 12, 13, 18, and 23. Now, the negatives aren't going to matter because we're going to do this step where we square the standard deviation. So to finish up here, we're going to square these. So I'm going to square negative 24. That basically means I'm taking negative 24 and timesing it by itself, which comes out to positive 576. So every negative is going to multiply by itself and become a positive. So we'll have no negative numbers here in this right column. So this comes out to 576 also. So if I take negative 21 and square it, it's going to be 441. Now, just a quick note, when you put it in the calculator, you need to include the parentheses. If you don't, and you just put negative 24 into the calculator squared with no parentheses, it's going to give you a negative answer because in the calculator, they think you're wanting to keep the whole number negative. So that would come out to negative 576 on the calculator. But you want to put the parentheses around it, and that'll make it a positive. And that's what we're actually doing. Negative 24 times negative 24. Okay, sorry, let's go ahead and keep going. So I happen to know that this one is 225, 121. Oops. 7 is 49, 36, 4 and 0. 1 squared is 1, 4, 25, 64, 81, 121, 144. I did have to put, oh no, 13 is 169. I know that one, but I don't know 18. 18 is 324 when you plug into the calculator. 23 is 529. Awesome. Okay, so what I'm going to do is sum these up. That's what the formula says. Now I'm going to add them all together, sum them. And that's what the table says to do. At the bottom, it says add up all the squared deviations. Take a second, add them all together. Make sure you get the answer I'm going to get. I am getting 3,490. Okay, so I rewrote the formula down here so we can use it to finish our calculation. So what we've just found, this number right here, the 3,490, is all of this numerator right there. So 3,490 is at the top. And at the bottom is n minus 1. So in this case, n is our sample size. And we happen to know from when we did this problem previously that there's 19 data values here. So I'm going to do 19 minus 1. And then I'm going to take the square root. So 19 minus 1, that is 18. And 3,490 divided by 18 is, and I'm going to approximate the decimal as I'm writing it down, though you should probably keep as much of it as you can. I'm getting 193.9, which comes out to 13.9. And that's very approximate. We've done a lot of rounding. Okay, so we want to compare this to what we would have gotten had we just taken the range and divided it by 4. So on the previous page, we calculated the range, and that was 47. And if we divide that number by 4, that's going to give me 11.75. So comparing that to the 13.9, clearly my 13.9 is bigger and more accurate. So the data is more spaced out than the other one implies. Okay, it's closer to 14 than it is to 12. And that's how we look at how spread out the data is. On average, a data value is about 14 away from the mean. And we use that information when we start talking about probabilities in chapter 4 and 5.